So I'm going to talk about end-to-same-end encryption, modularly augmenting an app with an efficient, portable, and blind cloud storage. Joint work with Chen from the Chinese Academy of Science, Ya-Nan and Qiang Tang from University of Sydney. And this actually a story which started with a real app that needed augmentation. So as we know, the cloud is pervasive, and people, app providers, and so on use the cloud storage, but then bad things can happen, and we learned a few years ago the incident of iCloud in which the cloud data was essentially stolen. It was through an account recovery mechanism. So like every new security mechanism is another attack vector. So somebody was doing account recovery, recovered the account of the celebrities and took their clear data. Anyway, so once the data is outsourced with no protection, the user is not there, and bad things can happen. And we want to secure the cloud data in a way that almost any provider, think about Dropbox or any cloud server, will be able to support it. So there's some simplicity element that involves in this, because you don't have the freedom to concoct your own solution. You have to use the server's API. But let's see attempts to secure the cloud storage. So encrypt data and store key on the user device. But this gives you no portability. Single device failure, you can fail. And why portability is like mobility, in which you can access the servers from any device. And people ask me, why do you need this? I always carry my phone. Well, the users of that app were not behaving the way you expect them. And it's good to have this portability anyway. Think about a service to a group which shares a password, and then they can come from different places. So portability is good, and we are talking about defining a service here that can have extensions and other uses. It's a kind of infrastructural element. Okay, so another way is to use the password to derive a key, because the user, supposedly, that's in apps, that's what you use in order to log into the apps. That's your source of security. But security is too weak. Offline attacks on password-based cryptographic keys are known. I'm not going to repeat it here. So a wise guy comes and says, enforce a 128-bit entropy password. But you've been attending USENIX security for years, and you know that the usability session is going to kill this solution. Yes? It's not usable. So then you do password encrypt key on device, which is, in some services, it's being used. But again, this gives you no portability. You're dependent upon a single device. And then store password encrypted key in the cloud. Security is too weak again, offline attacks. So all these solutions don't seem to work if you want security and usability. In security, I mean encrypt the data with a strong key against offline attacks. And we want this portability that I explained before. You can come from anywhere, naked, only with your password in your head. And if the app is on the device, you want to use it, to log into it and use it. And two other requirements are efficiency and system friendliness. But just these requirements by themselves of portability, and user has only his password, and then you have to store things securely. This already shows that one server solution seems hopeless. Actually, it may remind people of Pake, and there is a way to implement with this primitive Pake, and then Pake we know that you cannot do without a dedicated public key and other mechanisms, and therefore it contradicts efficiency, simplicity, and system friendliness, which we want, because we want it usable, and we want to use existing APIs to build it, and so it becomes interesting to do it, and in the sense that, you know, typically in cryptography, you come up with a mechanism and you're sophisticated and you use like almost the latest cryptographic tools that have been just proven secure in the last crypto conference. But here we kind of, it's Zen minimalism. It's what the API gives you, you have to work with it. So in a sense, we have to break the box. So the difficulty mainly comes from the setting, one client, one cloud. So as I told you, this started in industry within an app company. And the idea was that, and one thing in translating cryptographic solutions to actual deployment is combining the theory, the knowledge of the theory, the knowledge of systems need, and exploiting the architecture. And here the architecture, so a combination of these three, here the architecture played well for us because there are some other servers, like the app company servers, can be used. They are different than the cloud server. So let's call it the app server. So we don't necessarily have just one client, one cloud, but we have extra, at least one extra server in the puzzle, and we should use it. So what is the state of the art with two servers? You have two servers, and you want to solve kind of the problem of depositing information in the server that the server does not read, and then you can read it back. This is the end to same end. You put it in the server and you take it back to yourself, maybe in another device, but it's from you to yourself via the cloud, and the cloud should stay blind. So, of course, with two servers, we can implement a general MPC to solve such a problem, or even more efficiently, password-protected secret sharing was designed to solve these things. But those are, you know, you start to design MPC and all you have is TLS to a server, and of course, and to the other server. And of course, you can play the MPC game, but it's going to be very costly, and it's not the right solution, most likely, from many other, from performance perspective primarily, but from many other ways and reasons. And these are incompatible with really plain cloud storage, because what Dropbox gives you is TLS interface. Log in, you're in the session, send me data. You're in the session, take your data. That's the interface. Log in, retrieve, deposit. And this gives an interesting problem. In mathematics, people like to simplify and have simple solutions and so on. Here, the simplicity comes, the framework is the framework of the API, of what the servers provide. And many times in solutions, people ignore this aspect because it's somewhere hidden in the system. I have a great primitive, but it doesn't use the existing API. So maybe in 20 years, I will be able to use it. But this problem, as I originally solved it, was meant to be yesterday's solution. It was urgent. So, and of course the expenses and hard to migrate data to other clouds. You know, maybe you have an agreement with a cloud and they implement your great protocol. But then you want to migrate the data to another cloud, which you didn't negotiate a new API. So you have to start afresh. You know, there are many roadblocks if you don't build your solution based on existing APIs in existing servers. With your own servers, you can play. With your own app, you can play, but you know, it's harder with service providers, cloud service providers, and storage service providers. So what we want is secure and usable cloud storage with the most basic questions, and there was no viable solution. So we need to solve it. So the goal is to upgrade an existing app that has plain storage in the cloud with secure and usable cloud storage, so that you encrypt it with a strong key, the server doesn't get it, it's portable, as I said, the user is mobile and can come from anywhere. It's efficient, we want to use symmetric key crypto, we don't want to start heavy protocols. And system-friendly. System-friendly is a concise way to say it's deployable on existing cloud storage, it's compatible with standard tools, and built-in app that has a password-based login and so on. So I'll give you the high-level overview of these are the players, the cloud storage. On the left side, the user in the middle, all it has is its password, and the app server from the app company. And now you want to solve it, and what do you want? You want to deposit storage, your storage in encrypted form to the cloud server, and in order to do it, you need to have authentication, so to build authenticated channel between client and each server. And then you want to exploit the fact that you have two servers and kind of secret share the data encryption key MK along the three entities, so that you need what's in the cloud server, what's in the app server, and the password in order to recover it. And then you need to encrypt and upload the data in the cloud server. And the result that you want is a semantically secure solution, even against corrupt server, meaning servers that try to impersonate the users, and you get the best possible security, and you get the best possible security even if the two servers collude, then you at least get the password protection, okay, as a mitigation. You cannot have anything else because that's the only advantage of the client over the servers. And then you need to do retrieval, authenticate, then reconstruct. And I will just briefly mention the solution. So server authentication using TLS. The challenge is client authentication, and for this, we can only use one password to be compatible with the app. And okay, so we want to defeat the offline attack from corrupt servers. And the main idea here is to leverage one server to help log in the other server. You have the two of them, use them against each other in some sense. So in this, We use secret key at one server to change the password to password 1. Then we use password 1 to log in into the other server, the storage server. And then we draw a random number R1, and with it encrypt the password, have password 2, and put R1 in the cloud server as part of the TLS session, and put the login with this password 2 in the company server. And then you do secret sharing for data encryption, so you come up with a random key, and again you generate a key 1 derived from the password, and some R2, and you generate the ciphertext. And you kind of secret share in the most obvious way. You send the ciphertext to the cloud under the TLS server, and you send the random number R2, and the ciphertext you send to, the ciphertext of the key you send to the app server, and then you add integrity in the sense you want to protect it for integrity. So you derive this tau, which you can which demonstrate integrity of what you get, so the server cannot send you something else without integrity, and you can check it with the password and with the R2 that you get from the other server. And of course, based on all this, you can now put the encryption, and you can also, if you think about it, if you think about the secret sharing and the authentication that is helped by one side to do at the other side, in retrieving the information, you play the game kind of backwards. You get the right things, you compute the right things, and then it is expected to arrive from the other server, and you can check it, and you are sure of the integrity. For example, that you get the right key based on the fact that you got R2, and the app server gave you tau, and things like this, and these both prevent each server by itself from abusing the system and learning the data, and even if they are colluding, sorry, the lack of the password from the client, they will have to do exhaustive search on password, but that's the only tool that we have. And what's interesting is that it's very fast. I will end. It's very fast. It's almost like doing it without it, and that's it. So we propose secure, fully mobile and usable solutions, simplicity and efficiency. Sometimes simplicity and efficiency gives you a headache and you have to solve it. And we did it, and I think it's an interesting area to look at. Thank you very much.